welcome back. Today, we are going to tackle one of the most elegant, powerful, and, let's be honest, sometimes totally mind-bending ideas in all of computer science, recursion. We're going to go from a classic brain teaser all the way to the beautiful, hidden patterns of the natural world. Okay, so it all starts with a puzzle. This right here is the Tower of Hanoi, invented way back in 1883. The setup couldn't be simpler. You've got 3 poles and a bunch of disks stacked on one of them, from biggest on the bottom to smallest on top. The rules are even simpler. You can only move one disk at a time, and a bigger disk can never, ever sit on top of a smaller one. So here's the challenge for you. Your job is to get that entire stack from the starting pole on the left all the way over to the destination pole on the right. So what's the most efficient way to do it? Go ahead, pause, and think about it for a sec. It's trickier than it looks. The secret to solving this thing efficiently isn't just some clever trick. It's actually a really profound concept that unlocks a whole new way of thinking about problems. And that is the core of our puzzling introduction today. Now, if this is already starting to feel a little bit tricky, trust me, you're in very good company. Research from Virginia Tech confirms what pretty much every computer science student already knows. Recursion is famously one of the toughest concepts to really wrap your head around. But hey, that's exactly why we're here today, to break it all down. So what is this powerful idea? Well, the solution lies in recursion. At its heart, recursion is just this: solving a big problem by first solving a smaller version of the exact same problem. So instead of trying to tackle the whole monster at once, you just brick off a smaller, more manageable piece that looks just like it.
And check out how this applies to our puzzle. It's so elegant. To move a big tower of, say, n disks, you just follow 3 simple steps. First, you move the smaller tower of n-1 disks out of the way, onto the spare pole. Second, you move that one big bottom disk to its final home. And third, you just move that smaller tower from the spare pole right on top of it. See? The solution to moving a large tower is just knowing how to move a smaller tower. A perfect way to visualize this is to think of those Russian nesting dolls. You know the ones. Every time you open one up, you find a smaller, identical version of itself inside, and you keep going until you finally hit that tiny little one at the center that doesn't open. That's recursion in a nutshell. So we've got this great mental image of nesting dolls, but how do we get from a neat idea to something a computer can actually run with? How does this self-referential magic actually work? Well, that's what it means to start thinking recursively. I mean, it seems like a recipe for total chaos, right? A function is calling itself, which then calls itself again and again. How on earth does the machine remember where it is in the process and what it's supposed to do next without getting hopelessly confused? The answer is a really beautiful and simple mechanism called the call stack. You can think of it like the computer's short-term memory, or maybe like its to-do list. Every single time a function gets called, the computer basically writes down the details on a little note that's called a frame and slaps it on top of a stack of other notes. So as our Tower of Hanoi function calls itself to move a smaller tower, boom, a new frame is added to the top of the stack. And this happens over and over, so the stack gets taller and taller and taller. It only starts to shrink when a function finally finishes its job, returns a result, and its frame is popped right off the top. Now, this system is incredibly effective, but it has one critical limitation. So let's pop the hood for a minute and see what happens when we push that limit a little too far. Oh yeah, for anyone who's ever written code, this error message is the stuff of nightmares. This is a stack overflow, and it's the classic sign that your recursive function has gone completely off the rails. See, that memory lane we talked about? It isn't infinite. The stack has a real physical size limit. In Chrome's JavaScript engine, for example, it can handle roughly 10,000 function calls. If your recursion tries to pile on more frames than that, the whole system just throws its hands up to prevent a total crash. So what causes this disastrous overflow? Well, it almost always comes down to one of 3 very common, very human mistakes. Let's walk through them. Okay, mistake number 1, the big one, is a missing base case. The base case is your stop sign. It's the condition that tells the function, okay, we're done, stop calling yourself. In our nesting doll analogy, it's that tiniest doll. If you don't have one, the function will just call itself forever, piling frames onto the stack until it all comes crashing down. The second pitfall is a little sneakier. You might have a base case, but you forget the return keyword.
So when the function finally hits that stop condition, it doesn't actually send a result back up the chain. The chain of command gets broken, the stack doesn't unwind properly, and the whole thing just falls apart.
And finally, the third common mistake is just making the wrong recursive call. Remember, each call has to get you one step closer to your base case. If your function is supposed to work on a smaller problem, but you accidentally call it with the same parameters again, well, you're not making any progress. You're just running in place until you completely exhaust the stack.
So, now that we've navigated all the ways recursion can go wrong, let's pivot. Because when it goes right, it doesn't just solve problems. It reveals these profound and beautiful structures that are hidden all around us, moving us way beyond these common pitfalls.
Let's go all the way back to our Tower of Hanoi puzzle. What you're looking at here is a map of every single possible configuration for a 4-disk puzzle. Each little point is one way the disks can be arranged, and each line is a single legal move. Solving the puzzle is really just finding the shortest path from the start point to the end point on this map. But if we step back and just look at the overall shape of this entire map of possibilities, something absolutely amazing starts to emerge from all that complexity. It's a perfect Sierpinski triangle. It's a famous fractal, a shape that has this infinite repeating structure inside of it. The solution to a simple puzzle contains the blueprint for infinite complexity. How cool is that? And that's because fractals are basically recursion made visible. They're just patterns that repeat themselves at smaller and smaller scales. And they're not just some mathematical oddity, they are literally everywhere in nature. I mean, just think about a tree branch. It looks like a miniature tree, and it sprouts its own smaller branches that also look like the tree. It's the same pattern over and over. So from a simple puzzle to the very structure of a tree, recursion connects pure logic to the fundamental patterns of the universe. Which leaves us with one final thought to ponder. What other huge, complex problems out there could be simplified, or what other hidden patterns could be revealed if we just trained ourselves to look for the smaller version of the problem hiding right inside?